Welcome everyone to a new video. So this video is going to be a little different from my normal videos. So in this video, in fact, this is going to be a series of videos in which I'm going to be talking about the medicinal chemistry. So it has been seen that in many universities, medicinal chemistry course is being taught at the master's level, and this is one of the most important chapters that the chemistry of the antibacterial agents. So I thought that it would be a good idea to cover the various types of antibacterial agents along with their mechanisms and their action, and try to understand them. And medicinal chemistry can be so fascinating, and this is what I will try to convey you guys through my video. So everything that I'm going to discuss in this video has been taken from the book, which is an introduction to medicinal chemistry by Graham Patrick. If you are someone who wants to study medicinal chemistry, and then this is the go-to book, I highly recommend you guys this particular book. Okay, so what are we going to study in this particular video? Of course, we are going to talk about the sulfur drug. So this is the part one of the video, which is based on the antibacterial agents. Okay, so let's see what are we going to see in this particular video, or what are so the content of the video is going to be, first of all, we are going to briefly talk about the history of the antibacterial agents, and then we are going to have a brief look at the bacterial cell, what are the gram positive, what are the gram negative bacteria, and the mechanism of antibacterial action. Means what are the various mechanism, or what are the various way by which antibacterial agents act. Okay, and then we will look at the sulfur drugs, their SAR studies. SAR studies means structure activity relationship studies, means which are the functionalities that are absolutely important for these sulfur drug to act the way they do. And then we are going to look at one or two new breeds of sulfur drugs. And then, of course, the most important thing, the mechanism of the action, how do they actually act, and then the example. So in this video, first of all, in this slide, we're going to talk about the history of the antibacterial agent. So in fact, it is one of the great success stories of medicinal chemistry in the past 100 years. You cannot even imagine, 100 years back, people used to die because of simple bacterial infection. We have heard stories of, plague wiping out the entire cities, millions of death in a matter of, months, or, an year. Even today, if we see the tuberculosis in it caused almost 2 million deaths in 2000, and there are many children that are dying due to the respiratory infections. And these deaths are mostly from the African and the Asian nations. And then there are other 1.4 million children that are dying from the gut infections and the diarrhea related infections. So all these are bacteria related diseases, and even in the current generation, number of people are dying because of that. Now, because of that, you must have heard stories that the government are now putting a lot of funding into the research and development of various antibacterial agents, because they want the various institution to come up with the potential leads which can be useful to deal with the super bugs that we are going to encounter in the coming years. Okay, so let us look at the first drug. Was the first drug that was developed in 1910. It was an arsenic based drug. Before 1910, people used to mostly rely on various herbs and other type of you can say medicines. Mostly they were derived from the nature. So this was the first man-made drug, which was arsenic based drug, and it was developed in 1910. It did not had a wide range of bacterial activity. In fact, it was effective against the protozoal disease of sleep sickness and against the syphilis. But over a while, after 1945, we know that penicillin completely revolutionized the way we see how the antibacterial drug act. Okay, so this was used for quite a while, and this was arsenic based. In 1934, I mean, there was a gap of, let's say, 20 years. During this while, no antibacterial drug was developed, and then in 1934, proflavin, which is nothing but an acridine based drug, it was found to be very very effective in treating bacterial infection that resulted from deep surface wound, but it was too toxic when you simply inject it in your blood vein. So it means it cannot be carried through the blood streams. So it can only be applied onto the surface where the wound is. And then in 1935, in the subsequent year, there was a development of drug which is called protonsil, which is nothing but an initiation of the sulfa drugs, or which would be called is sulfonamides, and it was effective against the streptococcal infection in vivo. Okay, in vivo, what do I mean by that? That inside the body, outside the body, in vitro, it has absolutely zero activity, and we'll try and see why is that so. And okay, so this was the development from 1910 to 1935, and after that we understand that penicillin came along, and it completely revolutionized the way the antibacterial agents worked. And it just, even for the simplest of bacterial infection, doctor used to inject penicillin into the body, and it proved very effective. But it had its downsides, which is what we are going to learn in the part 2 of the video, when we are going to discuss of the chemistry of the penicillin. But for now, it is very important thing to understand that what is so special about the bacterial cell, that made it very easier for us to target it. It is simply due to the fact that the bacterial cell and the animal cell, by animal cell I mean the cell with which we are made up of, they are quite distinct, they are different in nature, their morphology is different, as a result of which we can simply target the bacterial cell. Okay, for example, the bacterial cell, it does not have a defined nucleus, whereas animal cell has. I mean, animal cell contain various organelles like mitochondria, endoplasmic reticulum, and other things. Whereas bacterial cell is quite simple; it doesn't have all these mitochondria and all. Apart from that, we get variety of vitamins or minerals from our diet, whereas the bacteria has to utilize various enzymes to make its own food. So that makes it easier for us to synthesize. And the bacterial cell has what we call as a cell membrane and a cell wall, whereas we do not have the cell wall, we only have the cell membrane. So these are the various properties of various things, using which we can synthesize, or we can target the bacterial cell, and with minimal to no reaction on the animal cells. Before going ahead, we must have heard about the gram positive and gram negative bacteria. These are nothing but two types of bacterial cell, depending upon the kind of cell wall it has. For example, in the gram positive bacteria, it is a thick walled. The cell membrane is quite thick. Okay, and it is almost 20 to 40 armstrong. And when you stain it with the dye, which is the crystal violet dye, then they turn purple. So that is, since they turn purple, that is why it is called gram positive. And if we see, what do we have? We have a plasma membrane, and then in between we have is what is called as a periplasmic space. So this is kind of a plasma, and on the outside what we have is a cell membrane that is made up of peptidoglycan layer. So this is nothing but peptidoglycan means it is peptide. Okay, peptide, that is amide bond plus various peptides, various amino acids, or it means we are talking about which are joined together with the various types of sugars. Okay, so that is what it is made up of. Now, what does the gram negative bacteria mean? So negative bacteria had their cell wall is quite thin, so it's not that thick. But what they do have is an extra outer layer, which is made up of lipopolysaccharides. Okay, so as a result of which we can clearly understand, this gives these gives gram negative bacteria extra strength to survive those harsh condition, because they have this extra layer to protect them. As a result of which, when you stain them with the crystal violet dye, rather than turning purple, they just turn into pink. So that is one of the ways via which we distinct the gram positive bacteria from the gram negative bacteria. And it is the gram negative bacteria which are often more resistant to the antibacterial drugs, and because the drug has to penetrate this extra layer which is on the outside. Okay, and then we can clearly see there are two periplasmic space here, and this is outside is the extra layer that we are talking about. Okay, I hope you understood this. Now, this is the most important thing about the bacterial action. So here what we have is a complete diagram of a bacterial cell. Okay. So what do we have is this outer membrane, which is, again, as I said, that which is only present in the gram-negative bacteria. Okay. And then what we have is this is the periplasmic space, and this is the cell wall that we are talking about. And inside the cell wall, what we have is this is what we call as a plasma membrane, and then these are the various ribosomes, and these are the DNA and RNA material, which is very very important for them. And then we have enzyme. These enzymes are very very important for the bacteria to survive, because bacteria utilizes these enzymes to make up food, to make up, to carry out the various functions that it needs to do in order to replicate. So in order to develop drugs, these drugs can, target each and every sites. Okay. So here we are talking about the five mechanism by which they act. The first one is the inhibition of the cell wall, cell metabolism. What do I mean by inhibition of the cell metabolism? It means that okay, so the drug that act by, this way are also called the antimetabolites. So it means that they simply target the enzyme. So here what we are going to talk about is the sulfonamide, which are nothing but a sulfur drugs. And sulfur drugs, that is how they act. They act by inhibiting the cell metabolism. It means they are not letting these enzyme, grow. They are inhibiting, they are acting on the enzyme, which are very important, as I said, for the bacterial cell to grow, to make their own food, to carry out the various important functions. And then we are talking about the inhibition of the cell wall synthesis. Now what happens? So the drugs which inhibit the formation of the cell walls are penicillin, cephalosporin, and cyclosidine. So what do we mean by inhibition of cell wall synthesis? So when we are going to study about the, penicillin drug in the part 2 of the video, we will study this in more detail. Now we can clearly understand if this cell wall synthesis is inhibited. So it means that the water can easily enter into the cell, as a result of which, cell is going to swell, and it is going to die because of the cell bursting, or we can call it the cell lysis, right? So these are the three drugs which act by inhibiting the bacterial cell wall synthesis. And then there is an interaction with the plasma membrane. So the drugs like polymycins, they interact with the plasma membrane, and what do they do actually? We clearly know that there is a very fine line of, ions inside and outside the plasma membrane. So what these polymycins do, they completely disrupt the flow of these cation inside and outside the ions, as a result of which the cell dies. And then there are drugs like which inhibit the protein synthesis. So protein synthesis, the drug which act by via this way are rifamycin and quinolones and aminoacridines. So we clearly know rifamycin is one of the drugs that is used to treat the tuberculosis. So the patients who are suffering from the tuberculosis, that is how so these drugs act upon the, DNA and RNA material of the of the cell. And then there is inhibition of nucleic acid transcription, the transcription and replication. So there are other processes like that as well. Okay. So we can clearly see from this particular slide that each and every site of the bacterial cell has been targeted, and depending upon the, severity of the situation, the particular drug is used. Okay. So as I said, in this particular video, or in this particular class, we are going to study about the sulfur drugs. So as I said, that these antibacterial agents act against the cell metabolism. Okay, so they are also called the antimetabolites. Now, what was found that when potential was administered in vitro, means when potential, it could not kill the bacteria when the test was done on the test tube. And the simple reason was that it needs to be metabolized. What do I mean by metabolism? Is that drug has to be broken down into small pieces. So when it was administered into the bacteria, then what happened in the small test intestine of a test animal, it gets converted into this what we call as a sulfanilamide. And it is actually this particular drug which acts as an efficient, drug to kill the various bacterial cell. So proton cell is an early example of a prodrug. What do we mean by prodrug? So this drug has absolutely, zero activity. It does not actually kill the bacteria. It does not, act against the particular receptor site. So only when it is metabolized into a particular, compound, only then it can, act as a drug. So that is why it is called a prodrug as well. So if we talk about the structure activity relationship, what do we mean by that? What are the absolute imperative, things that must be present in a drug, in a sulfur drug for it to be active? Then what they found that both these substitution means having these amino groups at this particular position. Okay, this is absolutely imperative. So this NH has to be either amine or it can be N acetate, because we know that N acetate, when it goes inside the body, then under harsh condition it can be hydrolyzed into the amine. So that is fine. So this R1 can only be hydrogen or it can be acetate. Second thing, this sulfonamide group and this amine moiety, it has to be para. This substitution has to be para. Having the sulfonamide moiety at ortho or meta is absolutely, kills the activity. Means such drugs has no antibacterial activity at all. So it means these two have to be para to each other. Third, third, that okay, sorry, I have talked about the third first. So I'm talking about the second point now. So what they said that these are the two important moiety that are absolutely important. Means having an amine moiety and having a sulfonamide moieties are absolutely important for them to be an efficient drug. Okay, and again the substitution has to be para. Apart from that, if you introduce any other functional group or at these position, means ortho, or meta position, the meta with respect to the amine and ortho with respect to the amine, okay, then they absolutely kill the activity. And it is because of this steric reason, that is what they are talking about. Second thing, the substitution at this particular position means the nitrogen that is attached to the sulfonyl group, it has to be primary or secondary. So it can be either NH2 or it can be some other substitution. Okay, it cannot be, you cannot put any other substitution at this particular position, but we can vary this. So from the structure activity relationship, what we can understand, so the only scope of improvement is placing having a various R group, means having an acetate or other functional groups, acetate or hydrogen or other functional group that can be easily hydrolyzed, or having different, moiety at this particular position. Apart from that, we cannot carry out any substitution on this particular molecule in order for them to be an effective sulfur. Now we're going to look at the new breed of the sulfur drugs. So we have kept all the points into the mind. We can clearly see there is no substitution at these position, and both the amine and the sulfonyl, they are para to each other. And here nitrogen, it has amine group, which is fine. Now what we have done, this is also secondary in this case. So what we have introduced is this aromatic moiety. So this is a drug called sulfadoxine. Okay, so when you take this particular drug sulfadoxine along with pyrimethamine, okay, which is called, so the combination of these two is called phenidisar, and it is used to treat the malaria. So we can clearly understand then how a combination of drugs can be very effective against the diseases like malaria. Apart from that, sulfur drugs, all the sulfur drugs that we are talking about, they are used to treat the UTI, urinary tract infections. They are used in eye lotion. Sometimes you must have seen the doctor gives us these eye lotions whenever we have these eye infections. So they are very important in that. Treatment of mucous membranes that is inside our gut, and that other type of gut infections. So sulfur drugs are very effective against the treatment of these type of diseases. These are the various important applications of sulfur drugs. Now we come to the most important part of this entire video. What is the mechanism of action of these sulfur drugs? Okay, before going ahead, I must tell you these two small definitions that you are going to study over the period of time, that you are going to hear about in the medicinal chemistry, that is the bacteriostatic or bactericidal. Okay, so any antibacterial agent which inhibits the cell growth. So it means what it is doing, it is not killing the bacteria, it is just inhibiting its growth. So they are called bacteriostatic. But if a drug which is like penicillin, obviously it is killing a bacterial cell, then it is called bactericidal. So any drug which kills the bacteria is called bactericidal. So any drug which is antibacterial agent I'm talking about, which inhibits this cell growth, is called bacteriostatic. Okay. So now coming back to the mechanism of the reaction. Now what happens? This is the entire cycle. This is a so what we are generating is this coenzyme tetrahydrofolates. For the time being, just concentrate on this tetrahydrofolate, and this is the sequence via which it is synthesized. So this is the biosynthesis of tetrahydrofolate. So what happens in the first step? We can clearly see that there is a reaction with the para-aminobenzoic acid, and it is this dihydropetroate synthetase. This is the enzyme which felicitates this attack of para-aminobenzoic acid on this moiety. So what do we get is this dihydropetroate, and which is treated with the glutamic acid. So this is what we end up getting, and then in the subsequent step, in the presence of the other enzyme, it gives the tetrahydrofolate, which is a coenzyme. So if you have heard about the coenzyme, we know these coenzymes are very, very important because for the synthesis of various important precursors in the human cell as well in the bacterial cell. So this tetrahydrofolate, this is very, very important cofactor, and the reason being, it just provides the one carbon. It provides the one carbon unit, which is very, very important, for the synthesis of pyrimidine nucleic acid base. Okay, which subsequently is required for the DNA synthesis. Now you can understand the importance of this tetrahydrofolate. Both human cell and both bacterial cell, both of them, they require this tetrahydrofolate. Okay, because again I'm reiterating this point. Why? Because this cofactor enzyme, it provides this one carbon unit that is required for the pyrimidine nucleic acid base, which subsequently is required for the DNA synthesis. So it means that if we can somehow inhibit the formation of this tetrahydrofolate, then we can clearly inhibit the formation of the DNA, or we can inhibit the formation of the pyrimidine base, and then subsequently the cell can no longer grow, it will not divide. So that is how we inhibit the cell growth. That is how this particular drug acts. Now what does this sulfonamide drug do? Okay, just before going ahead, there is one more drug which is trimethoprim, which is what we are going to see in the next slide. So they act upon this particular enzyme. So there are two stages. One is this stage, the other is this particular stage where we can act upon and stop the bacterial cell growth. So now let's just putting a attention onto this particular step. Now what we said, that para-aminobenzoic acid, it clearly comes and attacks in presence of this particular enzyme. Now these sulfonamide drugs, they act as a reversible inhibition. What do we mean by that reversible inhibition? It means that these sulfonamide drugs, they act as a competitive inhibitor, means they compete with this para-aminobenzoic acid to get itself attached to this pyrimidine base. That is how it does. Now if that is the case, then whatever compound that we are going to form, it is not going to undergo it is not going to lead to the formation of the tetrahydrofolate, as a result of which we are going to clearly block it. In the next slide we are going to see how it competes. But by just simply looking at this particular slide, there are a few questions that you must be thinking about. Let's just try and look at those questions. Okay, before going ahead to those particular questions, let me again just reiterate few points that I made. Okay, so the important thing that you must understand, that it this tetrahydrofolate is a coenzyme that is very, very important, that is required. It provides one carbon, okay, for the synthesis of pyrimidine nucleic acid base, which is required for the DNA synthesis. And this tetrahydrofolate is important both for human cell and for the bacterial cell. Okay, somehow if we can inhibit the formation of this tetrahydrofolate, then we are preventing the cell from growing and dividing. So that is how this sulfonamide drug, which act as a competitive enzyme inhibitor. Competitive means it is competing. Okay, it is competing to inhibit this, and we are blocking the tetrahydrofolate in the bacterial cell. Okay, there are a few questions that you might be thinking. Let us just try and see. Okay, the first important thing that you must be thinking, that tetrahydrofolate is clearly necessary for the survival of the bacterial cell, but it is also vital for the survival of human cell. So why sulfur drugs are not toxic to human? Because this is exactly what I said, that yes, it is required for the both human cell and the bacterial cell. For both of them, they are required. Now, the answer is that basically a human cell, we basically in our cell we synthesize tetrahydrofolate in a completely different manner, and we do not rely on this enzyme. We do not contain the enzyme dihydropetroid synthetase. We do not have that. So, in fact, in our cell, we synthesize our tetrahydrofolate from folic acid. But to and from where do we get the folic acid? We get it from our diet, from the vitamins, and then with the help of the various transport protein, it is brought across the cell membrane. Since the method of generation of tetrahydrofolate is completely different, so that is why the human cells are left untouched when you treat it with the sulfur drug. Now comes the question number two. Okay, so if human cell can acquire the folic acid from the diet, why can't the bacterial cell, which are infecting a human body, do the same? It's absolutely, it's a valid question that you guys have, and then they can also acquire it. The thing is that the bacterial cell, they do not have the necessary transport protein. This is very, very important. Okay, they do not have the necessary transport protein which are required to bring the folic acid across the membrane. So that is why they had to rely on the enzymes that they do. So if we sum up the entire things, why the sulfonamides are very, very important drugs, why sulfonamides are effective, why they were successful, it is because of the two metabolic differences in the mammalian and the bacterial cell. First is bacterial cell have a susceptible enzyme which is not present in the mammalian cell. Second thing is bacterial cell, they lack this transport protein that would allow them to acquire the folic acid from outside the cell. So because of these 2 points, we were able to successfully synthesize the sulfonamide or the sulfur drug. Now let us just try and see how does it inhibit the action. Okay, so what happens, this is the, okay, here what we am showing is the actual enzyme activated site. This is the actual site of this dihydropetroid synthetase. Okay, so what we had is this para-aminobenzoic acid. So this is how it just clearly sits into the active site. So there's a van der Waal interaction of these aromatic moiety, and then there's a hydrogen bonding at these side, and there's an ionic bond. If we clearly see the sulfonamide drugs, what they do, they mimic the action of this para-aminobenzoic acid. And why, how do they do so? Now we can clearly understand why do we need a free NH2. Okay, because they also undergo hydrogen bonding, and these benzene moiety, they undergoes van der Waal interaction. There's a van der Waal interaction, and this sulfonamide moiety, okay, this sulfonamide, they undergoes the ionic bond. So that is how the sulfonamide drugs, they prevent the cell from growing by mimicking the action of the para-aminobenzoic acid. Okay, so in a way what they are doing, it is fooling the enzyme. Okay, so what the enzyme thinks when the sulfonamide drugs reaches, enzyme thinks it is para-aminobenzoic acid, but in reality it is this sulfonamide drugs. And once this sulfonamide drugs gets into the active site, then you can clearly imagine, once it gets into the active site, then this this particular para-aminobenzoic acid cannot enter it, because for the bacterial cell, for the enzyme, it is the same kind of interaction that it is experiencing. Okay, so that is how this is acting. Now we are talking, we'll see the few more examples. So I talked about the trimethoprime. So this is also, a very, very effective antimicrobial drug. So this is the almost, 100,000 times more effective against the, bacterial enzyme. So, but it doesn't have the sulfonamide moiety. So these are the other antimetabolites. So what do I mean by that? It means they inhibit the cell growth. Okay. And as you know that trimethoprime, this is given in conjugation with the sulfonamide drug, which is a sulfamethoxazole. So what when you mix these two drugs, what do we end up getting is this particular drug. So this is sulfamethoxazole. So this is what we end up generating, uh, cotrimooxazole. Okay, which is a very, very effective drug. And apart from that, we have these sulfones, which act as a very, very efficient anti-leprosy drugs. So they also act the same way in which the sulfonamide act, means they act against this dihydropetroid synthetase. So that is how this chemistry of the sulfur drug works. I hope you like the video. So this video was for students who are studying the medicinal chemistry in the universities. If you have any questions regarding this particular video, just don't forget to ask me this question. Okay. See you next time with part 2 of the video. Have a nice day. Thank you very much.